Okay, so when you're talking about the discriminant, it's just the part underneath the quadratic formula, so the b squared minus 4ac is the discriminant part. If the b squared minus 4ac is greater than 0, so if you get a positive answer, if you think about looking at this, you're going to be adding some positive value and subtracting some positive value. So no matter what you do, it's going to end up being a real value. If these are all real numbers, then my answer, I'm adding a real number, subtracting a real number, it's going to come out to be some real number. Okay? So when you have a positive discriminant, you're going to have 2 real roots. Okay? If I have 2 real roots, then that means this thing as a graph is going to cross the x-axis. And it's going to do it twice. So wherever that happens, I don't really know. No matter what happens, that means it is going to cross twice, regardless of whether it's facing up or facing down. If you have 2 real roots, that means it crosses the x-axis in 2 places that you can actually graph. Okay? So as far as conceptual questions, if they gave you, they could potentially say the discriminant is 34. What does that tell you? Well, that tells me that since it's positive, there are 2 real roots, and it's going to cross the x-axis twice. Because they could say the discriminant is 34. Which one of these graphs is possible? Right? So just kind of keep that in mind. It doesn't tell us anything about where it crosses the x-axis at all. It just tells us that it's going to cross twice. That's all it tells us, is that it's going to cross twice because there are 2 real roots. Now, if your discriminant value is going to be less than 0, that means that I have a negative underneath a square root. So if I have a negative underneath a square root, that means that this right here is going to have an I when I break it down. So that means I'm going to have complex, and since I'm adding a complex, an I value, and subtracting an I value, that means I have 2 complex roots. Okay, if I have 2 complex roots, that means as far as the graph goes, I am either below the x-axis facing down, so I never cross the x-axis, or I am above the x-axis facing up. Okay, wherever those things are shifted to. But I'm either below it facing down or above it facing up, which means I am never going to cross the x-axis. And again, this discriminant value does not tell us anything about where those are. We can't even draw complex roots on the Cartesian coordinate plane, right? We have to make a whole new plane just for complex numbers. They don't exist in this particular world. So when you're doing that, if they said, like, you know, the discriminant value is -4, that doesn't mean it crosses at 4 or -4 or 2 and -2, which is what I see a lot of. It means it doesn't actually cross at all, and there is no way to know where exactly the graph is just based off the discriminant. We just know that it's not crossing. The last option, so it's either bigger than 0, less than 0, or it could actually be 0. If your discriminant value is equal to 0, then that means there is 1 real root, and it has a multiplicity of 2. Multiplicity of 2 just means you get the exact same answer twice. Again, if you think about the logic of this, if this right here is 0, then I added 0, I subtracted 0, I just get the same exact answer twice. Adding 0 is the same as subtracting the 0 value. So if this thing right here is 0, then I just add 0, subtract 0, and so I just have this real part that I have to worry about, which is going to be what my root is. So if there's 1 real root, then the way that that looks on a graph is that it will touch at some x value and go back the other way. Okay, so if they said that my discriminant was 0, then I would be looking to match it with a graph that just touches and goes back the other way, because that's the only way you can have only 1 root if I'm looking at a quadratic. So it could come from the top, right? We could do the same thing, but come from the bottom. Answers could be positive, negative, none of that really matters, right? So it could be positive, I mean it matters, but not for this. But yeah, so it's going to touch and go back the other direction. Okay, so that's what all of the discriminant stuff is about. So let's kind of do one, and we'll talk about the discriminant and what does it tell us, and then what the roots will be. So let's say we have a function that is -3x squared plus 4x minus 7. Okay? So if I have something like that, and they ask me to identify, like, what is the discriminant and what does it tell us? So just start with the discriminant part, so just the b squared minus 4ac. We don't have to do the rest. There's no radical involved. There's no nothing involved. We're just looking at the piece under the radical of the b squared minus 4ac. So I'm just going to plug into that. So 4 squared minus 4 times negative 3 times negative 7. Okay, that would be 16. Negative 4 and negative 3 makes positive 12. Okay, and then 12 times negative 7 would be negative, not negative 68. Scratch that. Sorry, I skipped ahead. 14, negative 84, which equals negative 68. Okay, so that would be the discriminant, would be negative 68, which tells us that we have two complex roots. Okay, that radical value is negative, which means my answer will have an I value involved. Okay, so two complex roots, we definitely have an I value involved. So now if it asks me to find the roots, now we're going to use our quadratic formula. The nice thing is we've already done part of the work. We already found our discriminant value, so we can just plug that straight in. So x is equal to negative b plus and minus the square root of b squared minus 4ac, which we already found to be negative 68. So I'm just going to plug that value straight in. All divided by 2 times negative 3. Okay, so now we got to break down our radicals. So negative 68, first of all, the negative comes out as the I. I square root of 68 over negative 6. We'll do the split and simplify and all that stuff in a little bit. But we've got I square root of 68. So we do have to be able to break down our radicals. So here, let's kind of start a little bit of that review. So if I have the square root of 68, take your number, break it into its prime factors, or you can just stop whenever you get to perfect squares, however you like. If you aren't sure, just start with the fact that if it's even, you know it's divisible by 2. Okay, every even value is divisible by 2. So 2 goes into 6 3 times and into 8 4 times. Still even, so I know that 2 has to go in. 2 goes into 3 once and into 14 7 times. 17 is a prime number, so we can kind of stop there. Okay, all your pairs, that's what's going to come out of the radical, because the square root means what number multiplied by itself, so 2 times 2. Right, so we can take that 2 value out. Anything left over stays inside. If you need to, the ones that you've broken down, cross them out so you don't accidentally multiply those back in and put them back in, because the 34 is where we got the 2 and 17 from. So the way that this looks is 2 on the outside, 17 on the inside. So I've got x is equal to negative 4 plus or minus 2I square root 17. All of that is still divided by negative 6. Okay, so now comes the reducing part of this. So depending on what format they ask you to put it in, they may ask you to leave it here and just reduce it. You can only reduce if all 3 of them are divisible by the exact same value. Okay, so all 3 of them have to be divisible by the same value if you're going to reduce all as one fraction. If you split them, then you can reduce them separately. So we'll split them just in case they want it in A plus BI format. All right, then we could do the split there. So I'm going to do that. So x is equal to negative 4 over negative 6 plus and minus 2 square root of 7 over negative 6I. I'm just moving it into the A plus BI format, right? So I took the I, put it out here, and just left all the numbers there. Now, negative over negative is positive, and 4 6 becomes 2/3. This negative that is down here kind of gets eaten up by the plus minus, because if I were to move this to the front, my plus becomes a minus and my minus becomes a plus. So it really just kind of gets eaten up when you have a plus minus there. So I'm just going to get rid of it, and then 2 over 6 becomes 1 over 3. So 1 over 3. The square root of 7 is still there, and the I is still there. 17, yeah, sorry. Thank you. I don't know, apparently I just can't math. Right, square root of 17, my fault. Right, so 2 square root of 17, which just reduces down to 1/3, and the square root of 17 is still there, and the I is still there. So that would be in the A plus BI format, if that's what they ask for. So same thing right here, the 2 and the 6 reduced to 1 and 3. Yeah, the one's just implied. Good question. Hi. I'm going to do a couple more, just breaking down radicals, just to make sure we know how to do that. And then we'll kind of go from there. Okay, anytime there's a negative inside, you're just going to pull that out as an I. That does have to happen before you do anything else, so you just kind of pull that out first. You can do it all in one step, that's fine, but do make sure that that comes out before. If we're doing multiplication or something like that of radicals, you always pull the I value out first. And then from there, you're just breaking that down. So if you don't know what the square root of 64 is, most of you do, obviously go straight to what the square root of 64 is, but if you don't, go and start breaking these things down. Okay, so 2 and 32, 2 and 16, 16 breaks into 4 and 4. Anytime you get a set of 2s, you could really stop there and just pull the 4 out, but if you're not comfortable doing that, keep going until you have all prime values, and everything is totally and completely broken down. Okay, and then every set of 2 comes out and multiplies together. So outside of the radical, you multiply all of those values together. So this would be 2 times 2 times 2 times I. There is nothing left over, so there is no radical left over. So it would just be 8I, which again, most of you knew the square root of 64 is 8, but just in case you don't, you can always just break them down. Well, let me make sure I get one that. Alright, so let's say I have the square root of 135. Again, if it was negative, the negative just comes out as an I. But outside of that, so you just start breaking things down. So it ends in a 5. It doesn't end in a 2, but if it ends in a 5, then it's got to be divisible by 5. So we'll go 5, and then it goes into 13 twice, and then 35 7 times. Alright, which is 9 and 3. Again, I would stop here because I know that the square root of 9 is 3, so I could just stop there. But if you're not comfortable there, just break it down into all of its primes, which just means keep going until you literally can't break anything down because they're at their smallest, right? That would be their prime values. And then any set comes out. So this would move to the outside. And then anything that is not, you just multiply it back together and put it inside. Okay, that's really all there is to breaking down radicals. Not a whole lot more to it than that. Let's see. Let's do one more of those, and then we got one more thing to talk about, and then I'll let you guys work. So, square root of 252, right? So the negative comes out. That way we don't have to worry about it. And then we just start our breakdown. So 252, if you don't know what goes into it, again, it's even, so just start with that. So 2, which would go in 126. Okay, this is also even, so here we go, 2, which would go in 63. Okay, obviously divisible by 3, so 3 and 21. Only 1 would be 3 and 7. Okay, I got a set of 2's, I got a set of 3's, and I have a 7 left over. So these go out front and multiply, and then that guy stays in. Okay, so 2 times 3, so I would get 6i square root 7. We okay with that? Yeah? Okay. Okay, so if you can break down your radicals, that should clear up a whole lot of things for the most part. And then one more thing, and then we'll talk about something you need for the word problems, because I just removed the other thing. So when we're reducing our fraction, so if I end up somewhere like 2 plus or minus 4i square root of 6 over 2, or 4, or whatever. Okay? I think one of the most common mistakes that I see is that when we reduce this radical value as well. But this isn't really a 6, it's the square root of 6, which has some value of 2 point something, right? Because 2 squared is 4, 3 squared is 9, so somewhere in the middle of that is where we would find the square root of 6. So if you plug square root of 6 in a calculator, it's like 2 point something. So you cannot simplify radicals with whole numbers. Okay, so that's probably the most common mistake that I see as far as all that goes, is this would reduce down to 1, 2, 3, and 2. Right, but that's not how that works. The only thing that's going to reduce are the whole numbers together. So if I did my split here, 2/4 plus or minus 4i root 6 over 4, right, and then I can reduce just the whole numbers. So I would get 1/2. The 4 and 4 would cancel, and I would get the square root of 6i, or I root 6. Okay, and they'll tell you on Canvas what format that you want. Typically, if we have a radical, we do put our I in the front unless we have a whole fraction, because what we don't want is for it to look like it's inside of the radical. So we typically put our I in the front unless it's a whole fraction and it's easy to see that the I is out back. But when they do it, they're going to make it very specific about what it should look like for a final answer. Okay? So last thing that I need to talk about with you guys is the creating quadratics if you're given a root. So they could potentially give you something like, if 2 plus 3i is a root, write a quadratic equation in standard form. Honestly, they'll specifically say write quadratic equation, because this could also be a root of a polynomial of a higher degree. But essentially what they're looking for is for you to write an equation out of this one little root into standard form. But we can do that because one thing to note is that if 2 plus 3i is a root, then 2 minus 3i has to be a root. Okay? If one complex value is there, then its conjugate is also there every single time. And the reason why that happens, because if you look at your formula, square root b squared minus 4ac, all divided by 2a. If I'm looking at my quadratic formula, well, if I get so say I get 3i as an answer right here, once I do this thing, I get like the square root of -9, so I get 3i as my answer over here. I'm going to be adding that value and subtracting that value because of the plus minus in the quadratic. Okay, so the complex conjugate will always be there because all of the rest of the values are all exactly the same. So the only thing that's going to change is that plus and minus. So you will always have the complex conjugate. So if they give you one root, you know without a doubt that the complex conjugate of that has to be there. Okay, so the complex conjugate will be the other root. So they could just say, if 2 plus 3i is a root, what is another root? Then you know 2 minus 3i is the other root. Okay, so if they want us to take that and write that as standard form, well, if you think about the fact that, so normally if I had something like x squared plus 5x plus 6, right? The normal, if it factors, so we got y equals, right? So we would set it equal to 0. We would factor that thing. We would set each piece equal to 0. Okay? So if I know the roots, I can do the exact process backwards. Right? If I know what my roots are, which is what they're giving me, but if I know any of the roots, because this from Unit 5, they could do this as well with just regular roots, but if they give me roots, then I can take them and I can change them so that they're equal to 0, and then I can take those two pieces, move them back into factors, multiply it back out, and I can end up at the standard form. Okay, so we can do that process backwards. So that's what we're going to do with this guy. We're going to take our 2 plus 3i, we're going to say x is equal to 2 plus 3i, which means that x also has to equal to minus 3i. Those have to be two roots. So now I'm going to change these back so that they're equal to 0. So now x minus 2 minus 3i is 0. X minus 2 plus 3i is equal to 0. So now I've converted them back into what are now factors. So now I can take these things and plug them and say x minus 2 minus 3i times x minus 2 plus 3i equals 0. Okay, so we set them equal to x, move them so that they're now equal to 0, take those pieces, turn them into factors, and now we're going to FOIL that whole thing out. We're going to multiply that whole thing out. Okay, so remember that if you're multiplying 3 terms by 3 terms, so the x multiplies by all 3. The negative 2 multiplies by all 3, and the negative 3i multiplies by all 3. So here we go. So x times x is x squared. X times negative 2 is negative 2x. X times positive 3i is positive 3xi. Okay, now I'm going to move to the next one. I'm going to do negative 2 times all 3 of those. So negative 2 times x is negative 2x. Negative 2 times negative 2 is positive 4. Negative 2 times positive 3i is negative 6i. Okay, moving down to the last one by all 3. So negative 3i times x is negative 3xi. Negative 3i times negative 2 is positive 6i. And negative 3i times positive 3i is negative 9i squared. Looks horrendous, but most of that stuff cancels itself out. Positive 3xi, negative 3xi, those cancel. Negative 6i, positive 6i, those cancel. All of your I values should go away if you've done this correctly, because you're using the complex conjugate, so all of those middle terms should cancel each other out. Okay, the only one I'm left with is the I squared, which we then change to a negative 9 times negative 1, which makes positive 9. Okay, combine your like terms and you're there. X squared minus 4x, positive 4 and positive 9 makes positive 13. We're writing it as a standard form equation, so now it's equal to y. Yep, that would be our quadratic in standard form. Okay, factoring backwards.